All right, we would like to look at a situation where you have an integral with an argument involving x squared as a sum or difference of squares of one of these three forms. Usually it would be found within an exponent or within a root or within a quotient. So if I make any of the following substitutions, now notice when it's a squared minus x squared, we'd make the substitution, let x equal a sine theta, a squared plus x squared minus a squared, the following substitutions. What this would give us is a Pythagorean identity that we could then simplify into one specific term. For example, if I had something of the form, let's say 100 minus x squared, well, given this form, if I chose x to be, now think of 100 as 10 squared, if I chose x to be 10 sine theta, then 100 minus x squared would become 100 minus 100 sine squared theta. And after factoring out the 100, that would give me something of this form. Meaning I started with something that was a difference, and perhaps it was under a root or it was in a denominator. But after this substitution, I get something of a much smaller form, which makes it much, much easier. Now, in each of these cases, you'd have to remember that the dx would have to be established this way, okay? Sine, cosine. Here, dx would be a secant squared theta d theta, and here dx would be a secant theta tan theta d theta. And then that would go into the integrand as well. So let's look at some examples of these. Now, first example, let's consider I have the square root of 64 minus x squared over x squared dx. Now, if I had the chain rule factor, if I could do a simple u substitution, I would, but I can't because my argument, 64 minus x squared, I'd need a 2x sitting around. I don't have one. So this is of the form 8 squared minus x squared. So I will make the substitution, let x equal 8 sine theta, then dx will be 8 cos theta d theta. And I'll put in parentheses, that means that the sine of theta is simply x over 8. I'm going to need that at the end of the problem because we're going to do an integration involving only theta. At the end, I'm going to need to substitute back in terms of x, and that's probably going to be the roadmap that I use. So now this will become, based on this substitution, okay, that will be 64 minus 64 sine squared theta under the root over x squared, so 64 sine squared theta in the denominator, and then my chain rule factor, I'll have 8 cos theta all integrated with respect to theta. Now remember, d theta is not part of the quotient, and make sure this 8 cosine isn't part of the root. Now, when I simplify this, this is going to become the square root of 64 times the square of the cosine under the root. Because when I factor out the 64, I'll have 1 minus sine squared times 8 cos theta over 64 sine squared theta d theta. So right now I have an 8 cos theta times an 8 cos theta over a 64 sine squared theta. That would mean I have 64 cos squared theta on top, 64 sine squared theta on the bottom. So ultimately I have simply the square of the cotangent. Well, that's a much, much smaller, much simpler function than what I started with. The problem is we don't know the antiderivative of the square of the cotangent. We know the antiderivative of the square of the cosecant. So we'll simply use the Pythagorean identity, that being that cotan squared plus 1 is cosecant squared. So cotan squared must be cosecant squared minus 1. And then that gives us quite simply the antiderivative of the cosecant squared is the negative of the cotangent. The antiderivative of negative 1 d theta would just be minus theta plus c. We're done. The calculus is finished. The dilemma, I have an integral of x, I have an answer of theta. So how do we get our answer? Well, we do it the old-fashioned way, like we did in trig and pre-calculus. We're going to draw a triangle. There's our theta. I need to draw a triangle where the sine of theta is 8 over x, because that's how I made my substitution. So for me to do that, I would put the x here and the 8 here. So now the sine of theta, so katoa, which would make this side 64 minus x squared. Now, it's no coincidence that I see that root as part of the problem. So now when I substitute back, this is going to become, okay, the cotangent would be this position over this position. So that would be negative root 64 minus x squared over x minus theta. But what would theta be? Theta would be the inverse sine. So minus the inverse sine of x over 8, or 1/8 x plus c. And there is my final answer. Now, generally, the test would involve just differentiating this, although that would be kind of a nasty derivative. That's exactly how we would do the problem, and that's how we would check our answer. Okay. One of the keys, though, is drawing the simple triangle that comes directly from the substitution you made. You're essentially going to do that every time. So let's try another one. Okay, let's look at, how about the integral of 1 over x times the square root of 4 plus x squared dx. Now, at first glance, that integrand looks a little bit like an inverse secant, but inverse secant, I would need x squared minus 4. So we don't know any antiderivative formulas that look like this. So when I look at my substitution, I see something of the form 2 squared plus x squared. So that tells me the only substitution I'm going to consider is I'm going to let x equal 2 tan theta. Then my dx is 2 secant squared theta d theta. And going back to here, this means that tan theta is x over 2. So that's going to be the picture that I'm going to draw when I get to that point. So when I make this particular substitution, okay, I'm going to get 2 tan theta. Then under the root, I'm going to have 4 plus 4 tan squared theta. On the top, I'm going to have 2 secant squared theta, all integrated with respect to theta. Now, this part here under the root, 4 plus 4 tan squared, that's literally 4 secant squared. Okay, so this is going to become 2 secant squared theta on top, 2 tan theta, and then the square root of this would be 2 secant theta. So that would be 4 tan theta, secant theta, d theta. Okay, my constants cancel nicely. And so I'm going to have a 1/2 in front. But now what am I going to have in my integrand? Well, I'm going to lose that secant and one of these. So secant theta over tan theta. That's 1 over cosine over sine over cosine, which is the same as 1 over sine or cosecant. So this is simply cosecant theta. Now, we don't love cosecants and cotangents, but this is a simple antiderivative. We know the antiderivative here is going to be 1/2 the natural log of the cosecant theta minus the cotangent theta plus c. So once again, I'm completely finished with the calculus, but what I need now is a picture that will allow me to go back. And here's the roadmap once again. So when I draw my triangle, I'm going to draw a triangle such that the tangent of theta is x over 2. So that would mean x over 2, which would make this side here the square root of 2 squared plus x squared. And once again, we see that showing up in the integrand. So my answer will be 1/2 the natural log of. Now, sine is this over this, so cosecant is this over this. So that would be square root of 4 plus x squared over x minus cotangent, which would be this side over this side. So minus 2 over x. Now we notice we have the same denominator, so it's probably a little cleaner if we wrote it like this. 4 plus x squared minus 2 all over x plus c. That's probably a better answer right there, although the first answer is perfectly acceptable. So at this point, again, we get something much simpler. And notice we see some of the same terms showing up in the final answer. Let's try another one. All right, let's do one more. Let's consider the integral of, how about 1 over x squared times, how about x squared minus 9? I want to give one look at each type of substitution here. So in this situation, I see x squared minus 3 squared, but because it's x squared minus number squared, this time our substitution will involve the secant function. So we would say let x equal, again, this is x squared minus 3 squared. So we'll choose 3 secant theta. Then my dx will be 3 secant theta tan theta d theta. And like before, that gives us secant theta equals x over 3. And that's the key to drawing the correct triangle. So when I make this particular substitution, this one looks like it might be a little bit busier than the others. My denominator will be the square of x, so 9 secant squared theta, square root of 9 secant squared theta minus 9. And on the top, I'll have 3 secant theta tan theta, all integrated with respect to theta. Now this quantity right here, 9 secant squared minus 9 is 9 tan squared. So now my numerator, 3 secant theta tan theta, the square root of this will be 3 tan. So along with this would be 27 secant squared theta tan theta. Now again, the constants cancel nicely, so I'll have 1/9. But even better, I have a secant theta on top. I have a secant squared theta on the bottom. So the tangents cancel. That secant cancels with one of those, and I'm left with 1 over secant. But 1 over the secant of theta is simply the cosine of theta. So this one turns out to be a very simple antiderivative. This will just be 1/9 sine theta plus c. And again, we establish our triangle. You don't memorize, you just simply draw it. I want a picture where the secant of theta is x over 3. So cosine is this over this, so secant is this over this, which means this side here would be x squared minus 9. And again, I know I did it right. If for some reason I had a 9 minus x squared or an x squared plus 9, that wouldn't match the original integrand. That's probably an indication that there's an error. So all I have to do now is make the appropriate substitution back. So this will be 1/9. Sine of theta is this over this. So I'm going to have a root x squared minus 9 over x, or I can simply write that as x squared minus 9 over 9x, and then plus my arbitrary constant. So we've seen a look at 3 different types of trig substitutions, one involving the sine, one involving the tangent, one involving the secant. All of the substitutions themselves should be relatively simple. The question is the resulting integral going to be simple that you get? There's no guarantee, but if I make the appropriate substitution, the new integral should at least be much, much smaller and a lot less scary, actually.